hadn't seen Justin for some time, waited for him at the bar. He walks in with the hat and Hawaiian shirt. I said, hey, I had something to show you. He handed over a mathematical paper. Of course, Justin is the type of guy that would bring math to the bar. And I jokingly asked him, hey man, did you solve turbulence? To which he responded, yes, I believe I did.
Turbulence is everywhere. Every time we take a breath, it's turbulent air in, turbulent air out. A heart murmur, for instance, is turbulence in the heart. When you have your cup of coffee in the morning, the steam rising off of it and doing the swirling pattern, like that's turbulence. We see it in atmospheric flows, we see it in oceanic flows, we see it in interstellar gas clouds. It's the tendency of a fast-moving fluid to create these complicated swirling patterns in the flow.
Well, most people think of turbulence as what you experience in a plane. But a third of the world's energy consumption is dedicated to overcoming turbulence.
As the liquid goes by the shape, its direction of flow is changed, and this wastes power.
Nobel laureates, Richard Feynman, Werner Heisenberg, long acknowledged that turbulence was one of those problems that may never be solved. If we could predict turbulence and understand how to suppress it, it would be revolutionary.
The development of more complete streamlining will be the problem of engineers of tomorrow.
The reason why this problem is so complicated is because the governing differential equation for fluid flows is called the Navier-Stokes equation. And it famously has a nonlinear term in it. And it's a nonlinear term that makes everything difficult. There's a century of amazing experimental data out there that's been replicated and verified and known to be correct. Really, what's needed is for someone to come along with a theory and put a model curve through the data.
Justin's always marched to his own tune. Well, first of all, Justin has never taken a fluid dynamics class in his life, or at least at the grad level. He is a mechanical engineer through and through. So on paper, he shouldn't be the guy that solves this. It seems almost offensive.
There's certainly many mathematicians that are far more proficient than I am. But it wasn't until retrospect that I realized that the way I was approaching the problem was a bit different than what had been done before. The scientific study of turbulence really began with Osborne Reynolds in the late 1800s. What he saw is that when you flow water through a pipe, slowly crank up the flow rate, there's a certain point in which the fluid changes from being laminar to all of a sudden abruptly changing to turbulent. And I was looking at the data on the transition from laminar to turbulent flow, and I sort of had an intuition that, there looks like there's some sort of trend here. Maybe there's something missing. Maybe there's a different way to approach it from the beginning that would be more fruitful. Maybe there's a different decomposition. For me, I don't really see symbols on a page. It's more like I see the landscape. So I see, mountains and valleys and textures, and spending enough time to see that picture. Once you see it, you can't unsee it. It took maybe about a year and a half. I had penned an exact closed-form theoretical framework for this problem.
What clinched it for me was seeing such a beautiful agreement between the framework he developed and over 100 years worth of data.
So far, we've had 100% success at comparing model and experiment. And this is really the test on whether this theory is real. Motivated by the theory, I started a company called Renco. At Renco, we're building a team to go after essentially all of the world's most important problems that are touched by turbulent fluids. So we should have a software package that is really accurate and predictive.
What would it look like to be able to know accurately what the weather was going to be in a month?
Or if you can find ways to modify the geometry of turbine blades to increase the energy yield by even like 1% or so, that translates into roughly 1% or so of world energy consumption.
So if it flows, this applies.
Turbulent flows are really messy and chaotic, but you can see that there is a kind of underlying order. It's almost like sort of being an explorer. With this framework in place, there's this wide open playground of things that we can do, and like we're just beginning to explore it.